Oh, отлично. So let's start. I would like to start by thanking the organizers for inviting me to give a talk on machine learning in astrophysics at this nice school. So my talk will be about machine learning in astrophysics, and I will follow the following plan. First of all, I would like to spell out why we use ML in astrophysics and what kind of tool it is considered to be in physics. Second, on example of telescope array and, if the time allows, Baikal-GVD experiments, I will discuss typical stages of creating neural networks, making sure that are reliable, and discuss related problems. So let's start. Why use ML in astrophysics? In any data analysis procedure, you have three main ingredients: data, program that analyzes the data, and prediction that is an output of the program. When using standard algorithm, program is a fixed code written and developed by a human. As such, it is interpretable and is a best approach possible if the problem at hand is exactly solvable. However, when it is hard to determine optimal features for classification, the machine learning comes in. It will be very hard, for instance, to write by hand optimal filters to identify what digit we are given. So in machine learning, program is an algorithm that learns on example to extract optimal features. That is to say that by learning, neural network finds optimal ways, and by analyzing data, it uses several filters with which were found to be best for analyzing the given data. In this sense, neural networks are programs that create optimal algorithm. And here we have a trade-off. On the standard side, we have interpretable algorithm. That is, we make by hand algorithm. We know which parameters it uses, and we know how interpret its results. On the other hand, we have powerful black box, powerful in the sense that it can solve a lot of problems, make very good predictions, but nonetheless it is a black box. It is very hard to understand which kind of data neural network analyzes, and additionally we must make sure, as we are dealing with physics, that these parameters are physically interpretable. And this is an important aspect on which I will discuss later in detail. So let's start with the experiment telescope array. It studies cosmic rays. What are cosmic rays? In galaxy, we have a lot of objects such as black holes, active galaxies, etc., which emit different particles: protons, nitrogen, iron, and sometimes photons. After traveling through the universe, these particles sometimes enter Earth's atmosphere, where they start producing primary particles. There are, for a typical shower, there may be thousands, if not millions, of secondary particles. Some of these particles reach Earth's atmosphere. We detect them, and based on this detection, we would like to infer properties of these primary particles which enter Earth's atmosphere. And by doing so, we indirectly study galaxies and models of their evolution, and indirectly has access to very high energies, as not typical, but often primary particles have energies some orders of magnitude higher that are available for study at Large Hadron Collider. In this sense, cosmic rays gives us perfect chance to study really very high energy physics. So here I have depicted an example of data recorded from the detectors of, sorry, there must be, yeah, I have missed one slide, sorry. So what is telescope array? Telescope array is the largest cosmic ray observatory in Northern Hemisphere. It covers approximately an area of 700 kilometers squared and includes 507 surface detectors, which are depicted here. An individual detector is depicted here, and you consider it just a tool that outputs a signal when a secondary particle coming from cosmic rays hits the detector. The higher the energy of the secondary particle is, the higher is the signal. So here are typical recordings of the detectors for a given event. The x-axis shows time, and the y-axis is used to depict detector coordinates. As you can see, this data is rather complex. In the sense it is stochastic, and it is very hard to directly apply it to directly use it to infer properties of primary particles, such as its energy, incoming direction, etc. And this is a place where machine learning comes in. So, and we have the goal. We would like to analyze data, the readings of the detector, by methods of machine learning. And the first stage, we should solve the following problem. What is the best way to represent the data? Well, you must say that here it is. You give us an image, let's analyze them. But it is arguably not the best representation. First, this data representation is sparse. There are a lot of zeros, and hence it will be hard for neural network to analyze this data. Secondly, the peaks in detectors readings rarely overlap, and hence to extract useful information, we have to use a lot of convolutional layers or use big kernels, which makes neural networks hard to train. So after some experiments, we came with the following solution. Consider a waveform that is readings of the detector, a given detector. So we cut all signals to last 128 beans, 20 nanoseconds each, and here we have represented it graphically. One can think about waveform as an image or as a sequence. It is a sequence, as it is a sequence of detector readings and time, and at the same time we can think about it as a one-dimensional image. And the later approach is much more useful because what we are seeing here are some peaks that we want to analyze their height, their number, the distance between them, etc. So the best approach to analyze this data is to use convolutional neural networks. And we make a small encoder, which is a convolutional neural network that takes an input, a waveform, and outputs signal features, which is a small dimensional vector. Okay, this is for an individual event, but for individual detector, sorry. How we analyze event as a whole. So we do the following. We take all detectors that have been activated during an event and order them according to their activation time. Then we pass individual waveforms through an encoder and thus obtain properties of these waveforms. As these detectors have been ordered according to the activation time, we can consider these properties as a time series. And hence we can apply a recurrent neural network to analyze this data. We use small LSTM cell, which one by one sees these properties, and at the end of the sequence, outputs error shower properties. This might be any error shower property that we are interested in, that is mass of the primary particle, its energy, or incoming angle. So to be concrete, here's a neural network architecture that we finally came up with for analyzing events. Here you can see I've been discussing this part, which is called temporal detector bundle, which takes all of the detector, passes it through the signal encoder, which outputs features of individual waveforms. Then we use LSTM to predict features of an event as a whole, which are further used to predict properties of the error shower. Okay, so suppose we have identified the optimal data representation. Then comes the next stage. To be concrete, suppose we would like to distinguish between photon-induced events and hadron-induced events. This problem is well posed, as the corresponding error showers which were detected are very different. And hence, we can train neural network to very well distinguish between these events. So let's output of our neural network be a number in the range 0, 1, so that 0 corresponds to hadron and 1 to the photon. Then we can take our test dataset and plot histograms of the predictions of our neural network. And then comes the question. We should somewhere put a threshold and call all the events to the right of this threshold photon-like, and to the left of this threshold hadron-like. But where should we put it exactly? In other words, what is the right balance between true and false positives? Of course, the answer to this question is task-specific. For our case, we know for sure that there will be very few photons in our data, and thus we have the goal of estimating the upper limit on photon flux. And in this case, we introduced procedure for optimizing the cuts, that is a threshold, by requiring stronger sensitivity in absence of photon in the data, which is roughly equivalent to minimizing the ratio of false photons to true photons. Would our goal be different? For instance, if we were aimed at estimating the lower bound of the photon flux, our procedure would be completely different, and we would be minimizing different quantity. So in most cases, after we formulated our goal and introduced a cut optimization procedure, we want to get as good metrics as possible. For this case, we were roughly interested in getting as small ratio of false photons to true photons as possible. This often requires introduction of special loss functions that can be either handmade or non-standard. For instance, in this case, we have used the so-known focal loss, which forces the tail of distributions near 0 and 1 to be very low. Okay, now we have identified the best data representation, know how we should analyze it, and we have set a procedure for setting a threshold for identifying photons and hadrons, and get the best results possible in terms of our metric of interest. Then comes the question: do we really? Are neural network predictions reliable? Reformulating, we must make sure that neural network is insensitive to unphysical details of our simulations. As we are studying cosmic rays, we cannot teach our neural network on real examples. On real data, we do not know what was the primary particle, what was its energy and the coming direction. However, what we can do, we can simulate these events and simulate detector responses. That is for a given energy primary, its energy and incoming direction, we can simulate detector response. However, these simulations are subject to uncertainty and errors that have several sources. For instance, in practice, we might have some not properly working detectors or not working at all. Then we have some simulation simplifications, specifics, etc., that might not really show the distribution of real data. And finally, we have limitations of simulating the hardware response. Surface detectors have some complex internal structure, and thus it is hard to reliably simulate their response. These problems should be addressed, and thus we must make sure that neural network predictions are indeed reliable. How can we do that? We must run cross-checks. For instance, if we have standard algorithm of, for example, reconstructing primary particle angle, we might compare neural network predictions and standard one. And if they are correlated, then neural network is insensitive to unphysical details. Another approach that we can take is to compare Monte Carlo simulated data and real data. For the case I'm considering, we were interested in estimating the photon flux. We know that there are very little photons in real data for sure. This implies that if we use real data depicted here in the green and plot histogram for its predictions, it must be very close to the predictions of protons that have been simulated, the red curve. After adjusting neural network parameters, we indeed make neural network, we indeed make these curves to be similar, and often these problems, the discrepancy between real data and Monte Carlo predictions can be solved by introducing various dropouts, by introducing various masks for indicating which of the detectors are not properly working and in which way. And finally, which we found to be most efficient, we sample random noise into the data so that neural network during training does not overfit to some unphysical specific details. And that's how we were able to get these distributions very close. So for now, I've been discussing a well-posed problem. Photon-induced events and hadron-induced events look very different. And correspondingly, we can train a neural network to distinguish between them very, very well. However, suppose that we want to identify primary particle. What was the primary particle for hadron events? Was it helium, nitrogen, iron, or proton? Well, we can train the same neural network to predict the logarithm of the primary particle mass and build a histogram for the predictions on the test data set. As you can see, these distributions overlap very much, and they are not centered around their true values. For instance, iron should be centered around 3, while its center here is around 2. This reflects the fact that the problem is not really well posed, because there are lots of sources of stochasticity and uncertainty in the problem. Namely, evolution of air shower is very stochastic. This implies that if we have the same particle entering atmosphere twice, absolutely the same particle, the same incoming angle, the same energy, etc., detector readings may differ very significantly. And secondly, the data that has been recorded by detectors may be very similar for different primaries. Again, due to the fact that evolution of air shower is very stochastic, and due to the fact also that the observables that can be measured do not really differ that much for different primaries such as proton, helium, and nitrogen. And if we train a neural network not in a regression regime, but in a classifier regime, in a 4-class model, when it predicts the type of the primary, proton, helium, nitrogen, and iron, we get only roughly 39% of success, which should be compared again 25% as random guessing. We cannot get higher accuracy, whatever we do, because it is an intrinsic problem of the task. The data is very stochastic. And even by introducing very complex and advanced machine learning techniques, you cannot get much higher accuracy than that. And for instance, to illustrate how bad is the situation, suppose we have an ensemble of events. Say we have 5,000 events that were only proton-induced, helium-induced, nitrogen-induced, or iron-induced. And we use our neural network to identify the fractions of primaries in this ensemble of events. So for protons, it would say that only 35% of protons are indeed protons. All other particles will be classified as helium, nitrogen, or iron. And the situation is the same for all other elements as well. So then the question comes, can we really improve our predictions by making use of the fact that we are interested, in fact, in considering ensembles of events and not in individual ones? That is, given, for instance, 10,000 events, we would like to infer the fractions of elements, primary elements in this ensemble, similar to this. And the answer is possible. And the answer is possible. We can make use of the statistics. Namely, we introduce the two-chain analysis where we're using two neural networks. First, we train classifier to predict the type of the primary particle. With rows is the parameters, and train a second neural network converter in the following way. We randomly sample 5,000 events. We pass each of them through the classifier, which outputs 4 numbers for each of the events, which corresponds to its prediction what was the primary particle. Then we get mean and standard deviations of these predictions, thus obtaining at 8 numbers. These 8 numbers are further passed through the converter, which is trained to output the true fractions of element in this ensemble. And this scheme of analysis turned out to be very useful. Here, for illustration, I have depicted an arbitrary ensemble, 41% of events of which were induced by proton, 19% by helium, 24% by nitrogen, and 16% by iron. If we use a single classifier to predict fractions of elements in an ensemble, we get absolutely unreliable and unsensible predictions. Almost it will say that the fractions of all particles are the same. If we use the confusion matrix approach, which is a linear algebra equivalent of our converter neural network, we get better predictions. Yet, if we use the converter, we can get the best predictions. We can evaluate our mean absolute error on test ensembles, and we find out that we have an absolute error of about 7%, which is great compared to previous results. So that was about telescope array. Let me now speak about Baikal-GVD experiment. Baikal-GVD is a neutrino telescope located in Lake Baikal, and worldwide there are only 2 experiments that have similar physical objectives. Namely, it is KM3net and IceCube, both of which has working volume of about 1 kilometer cubed, same as Baikal-GVD. So what are these experiments? This blue surface represents the surface of Lake Baikal. In Lake Baikal, the principal components of detectors are optical models that register light inside the water. Optical models are organized into strings, a vertical stack of optical models, and we have 36 optical models per string. In turn, strings are organized into clusters, nearly regular heptagons with additional string in the center. As of 2021, in Lake Baikal, we have 8 such clusters, and in what follows, I'm going to focus on analyzing data from one of these clusters. A typical event that can be registered by Baikal-GVD looks as follows. We have some particle propagating through the detector, and as it has high energy, it emits the so-known Cherenkov light. And this Cherenkov light is registered by optical models, and it leaves a trace on the detectors how the particle traveled through the detector. So then, given these readings, we might pose various tasks. For instance, we might be interested in inferring the energy of the primary particle, its incoming direction, etc. And the point I would like to stress is that for each of these tasks, the data representation, the optimal data representation, will be specific. Let me reformulate it. Data representation should be task specific. For instance, one way of representing the detector is to mimic its geometric structure. We introduce 3 by 3 by 36 parallelepiped, which mimics the structure of the detector. In each cell, we input detector readings, and by using three-dimensional convolution, we make analyze and events. Such a presentation of data will be optimal for inferring geometrical properties of events, such as incoming angle of a particle, etc. Another way of representing the data is causal one. Namely, we take all of the detectors that have been activated in an event and order them according to the activation times. And then this sequence can be analyzed either by one-dimensional convolutions or by recurrent neural networks. This representation makes use of the fact that signal hits related, that hits of interest that we, sorry, let me make a step back. As this detector is located in water, we have a lot of noise. We will have activations not only from the detectors that are along the line of propagation of the particle, but also some random noise here, 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 here. And such casual representation of the data makes use of the fact that signal hits originating due to the propagation of the particle would be clustered. And in this way, it will be much easier for a neural network to identify these signal hits and discriminate between signal and noise hits. And finally, we can represent an event as a graph. That is, each optical module will be represented as a vertex on a graph, and we should connect different vertices by lines, so that and we should provide a rule for saying which vertices are connected. For instance, we might say that for a given detector, it is connected to its, for instance, 4 or 5 nearest neighbors. And then we can use graph updating protocols such as graph convolutions or message passing graph neural networks to infer properties of such events. Such a presentation of the data will be most useful for inferring, again, geometrical properties such as incoming angle, and hopefully it will help us to identify the energy of an incoming particle with small error. So on this slide, I just would like to stress that in physics, we do not have some fixed way of thinking about the data. We have different ways of thinking about the data depending on the task. And one of the goals is to identify which data representation will be most efficient for a given task. So thank you for your attention. That was all I'd like to say. Of course, I haven't covered a lot of topics. For instance, such as use of invertible neural networks to infer posterior distribution of model parameters, or unsupervised clustering, which are both, these techniques are of interest in context of astrophysics, but I believe that I have highlighted some important details. Thank you.
Yeah, thank you for the presentation. Can you open slide with your first task with data from sensor? It was blue line with peaks, yes, like this. So you said that you used 1D convolutional here, yes?
Yes.
What do you think about the idea to proceed this like pictures with 2D convolutional layers? Kernels. I mean, according to my experience, sometimes it can be better to use it as pictures, yes.
Yeah, in fact, we are considering it as pictures, but they're one-dimensional. You do not have vertical dimension to it additionally, just a sequence of pixels, and the value of pixel identify the value which has been recorded by the detector.
Yes, 1D kernel, yes? What will happen if you will use 2D kernel? 3 by 3, for example.
We do not have additional dimensionals to use three-dimensional kernels. So this picture is essentially one-dimensional. So you can think of this, for instance, suppose these were just pixels and neglect this vertical axis, right? So suppose we have pixels one by one here. And then equivalent representation of this picture is that, for instance, here the pixel is black as the value of the signal is small, black, black, something like gray, black, black, gray, gray, black, white, etc.
Yeah.
We do have two channels of our detectors. As you can see here, there is blue and red lines. It is similar to RGB channels in the image, but nonetheless, this data representation is strictly one-dimensional.
Yeah, but if not to consider this data as a vector but as a matrix, you can use another kernel, yes?
Sorry?
Not 3D, but 2D, no?
In which way?
So like simple picture, I mean, for example.
It is simple picture.
Yes, like face, for example, yes?
No, we do not have second dimension. I can analyze two-dimensional kernels in this case. This is true. Because I have the second dimensional, which is used to, so for instance, on this axis, I will have signal from one of the detectors. On the second line, I will have detector readings of the other detector, etc., etc.
So this picture differ only by this y-axis we have.
Yes.
But on the previous picture, we also have this axis. So what's difference conceptual?
It's not a picture of face, right? If it, I do not really know how to formulate it. You can use two-dimensional convolutions or three-dimensional one, only in case when your data is two or three-dimensional, right? In our case, the data is intrinsically one-dimensional, just a sequence of records.
Okay, I still think it's possible, but never mind. Thank you.